Algebras. Welcome to your Chapter 12, Lesson 5 notes on translating or moving our exponential functions around the xy axes. And so we're kind of going to start by talking about the very basic function of f of x equals 2 to the x power. And this is our classic doubling function that we have graphed so many times at this point. So this is old hat to us. Okay, we've been doing this one for a while. But here's the deal. What I'm going to do is, since that's my basic function that I'm going to base things on, I'm going to call that my parent function. Okay, so I'm going to call that one my parent function. And I am going to move that depending on the additions to the equation I make. We're going to look at it in a general form, and we're going to look at it actually changing this graph. My color graphing calculator will be pretty helpful for us in these changes that we're making. Okay, so on my screen right now, I have my color graphing calculator. I'm just going to make it a little bit bigger so that we can see what I'm talking about. And what I'm going to do to start is I am going to type in 2 raised to the x power, which is my very basic parent function of my exponential functions. This is our classic doubling function. We're just going to remind ourselves what this looks like on the graph. And so, of course, we can see this is our asymptote coming up. We're as close to 0 down here as we can be without touching or crossing. So while that looks like it's right on the y equals 0 line, we all know it's not. It's just very, 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 very close. And then as we get closer to the y-axis, we get further from that. And as we go, then whoop, real quick, rapid increase, right? Okay, so that's our very basic parent function. Now what I'm going to do is I'm going to show you this function with the changes on the front in the pictures that we have. So the first change I'm going to make is I'm going to take this function and I'm going to add 3 in the exponent. So I arrow down to y2 and I type in 2 raised to the x plus 3 power. So I want that plus 3 in the exponent. So if you're working with an old TI-83, when you press your caret button, front parenthesis, x plus 3, end parenthesis, that's how your graphing calculator will know that you want all of this to be in the exponent. And now press graph to see them. Remember, my parent function, my blue, is my initial graph. What am I doing to that graph? Look at that. By adding 3 in the exponent, my graph has gone left 3 places. And you can tell that from the table of points. And think just based on this, right? Where did I see a y value of 8 on my original graph? It was at x value of 3. Now I see a y value of 8 at an x value of 0. Excuse me. That means that this graph moved left 3. So all those y points moved left 3. Okay? Or if you're talking about their actual x values, right? If I started out at 0, 1, and I'm looking for the y value at 1, look, it moved to -3, 1. And so that's what we're talking about a translate, a move over, a shift over. Okay? If you change the value in the exponent, you'll move left or right. Now, what's interesting about that is, let's look back at the exponent that I added. I added 3, right? Wouldn't you normally think that would add 3 on the x? Well, based on our work with vertex form back in chapter 11, actually we know that if something is in those parentheses, it's the opposite sign. It's the opposite sign. So it does the opposite thing that you think. And in this case, because it's a +3 in my exponent, I actually move left 3. Okay? Now, let's make the next change that we were asked to do on our paper, which is instead of the exponent having the change, so what I'm going to do is go up in my exponent and delete, delete. Now notice I've got this arrow, so I can come out of this and press +3. Now, instead of the exponent being changed, I'm actually going to add 3 to the end of the equation, okay? So if you're using a TI-83, when you hit your caret, press front parenthesis, X end parenthesis, then type your +3 so that your graphing calculator knows only the X is in the exponent. This +3 is not in the exponent. This is a change up and down. So when I press graph, here's my original. Look at this one. The y-intercept went up here. So that asymptote went up here. And now the asymptote is y equals 3. And how do I know that? If I press second in graph and I look at these values are approaching 3. Right? These values going backwards, and I'll just kind of arrow up backwards so you can see they're getting closer and closer and closer to 3. So that's how I know that y equals 3, that is the horizontal line that I cannot touch or cross. And then look at all these. These all are the same decimal value, but just 3 in front because we went up y-wise to 3. So all of these y's just added 3 to them, just added 3 to them, just added 3 to them, okay? When you add 3 to the end of the function, that's exactly what happens, is that you're adding 3 to that y value. So notice that is the correct sign of what we think should happen. So if I have a +3 at the end of my function now, my basic parent function, I'm moving up 3 with everything. Okay? So let's just look back at after that experiment here, let's just look back at what our worksheet is actually asking us to do. Scooch this guy over for now. Okay, what are we actually being asked to do right here? Well, here we have the original, and we call that the parent function. So calling something the parent function is just what are we basing our movement on, okay? So the parent function is our f of x equals 2 to the x power. And what happened when I added 3 in the exponent? Well, everything moved left 3. See that? So what changed in the equation? Added 3 in exponent. And what changed on the graph? The graph moved left 3. Over here, we added 3 at the end of the equation, right? So we added 3 at the end of the equation, and look, the whole deal moved up 3, including our asymptote is now y equals 3. That's now our invisible barrier that we cannot touch and cross. So what changed in the equation? We added 3 at the end. And what changes in the graph? The graph moved up 3. Okay? And when we discussed asymptotes back in the very beginning of this chapter, we said that an asymptote, and spell it correctly because it is on our paper enough places, asymptote, right? What is an asymptote? An invisible barrier that our function will not touch or cross. In exponential functions, the asymptote is part of the graph. So you do need to make sure you include the asymptote when you graph anything. It's always going to be a horizontal line in our exponential functions. Okay? Now, when we looked at these changes, okay, by adding 3 in the parentheses in this general form, what we took was we took f of x, and now it's equal to 2x plus 3 up here, right? Am I adding or subtracting anything right here? No. So that means my asymptote is y equals 0. In this form, when I did that, now my graph is f of x equals 2 raised to the x and then plus 3 at the end. So see how that plus 3 was not in the parentheses? That means I did not change the exponent. I just added 3 to the end of the function equation. And in this graph, our asymptote came out to be y equals 3 because all the y values had moved up 3, including that asymptote. So guess what this end number determines for us? Our invisible barrier we cannot touch or cross. Whatever this number is at the end of the function equation, y equals that is your asymptote. And we had talked about that in lesson 2. But again, it was a while ago, so it's good to review that, right? So now what we want to do is take our original parent function, which is still going to be this f of x equals 2 to the x power. We want to graph it, and then we want to make these two changes based on what I just showed you that will equal, okay? So first of all, let's just graph this original function right here, okay? And I'll graph the original function in blue since that's what I use most often, okay? So this guy will be f of x equals 2 to the x power, and that's our parent function. And again, the parent part of the function means that's what we're starting from, and any changes made to it are the next generation, quote unquote, okay? So let's start with this, and I actually already have the correct values I'm supposed to fill in, so let's just go to the graph and fill those in. I'll, of course, start with my y-intercept 0, 1, then 1, 2, 2, 4, 3, 8, and 4, 16. Now I can kind of go backwards with these fractional points, right? So negative 1, 1/2, negative 2, 1/4, and negative 3, 1/8. And we have done this so many times, I'm kind of moving here because we have graphed this exact function so many times in these notes and then in the homework. Now, again, I put my arrows right at the end. This arrow down here by the asymptote needs to be straight, and then we draw in our asymptote as a dotted line, and we'll label it ASY is y equals 0. And that, of course, for this graph is the invisible barrier we are not touching or crossing. So since this is the parent function, I'm going to label it f of x. Okay? Well, that's the first one. From here, now what we're going to do is we're going to make the appropriate changes based on the general form of the changes we look at. So in this case, f of x plus 2 is telling us we add in the exponent. So if we are adding or subtracting in the parentheses, that means you add or subtract that number in the exponent. So in order to get this match from our graphing calculator, we need to make that change in the exponent. So we've got our original function. Let's arrow down. Well, that's not going to happen unless I do this. There we go. Now we can have both be a little bit bigger. So there's my original parent function. Let's arrow down, clear this out, and type in the new function, which says we're adding 2 in the exponent. So 2 caret x plus 2. All of that needs to be in the exponent. So if you want to press graph to see it, you of course see our blue parent function. It looks like they have the same points for a while here, but then red raises way up before blue. That's because this entire function moved left 2. And I know that because I made that change in the exponent of adding 2. So now if f of x is plus 2, if f of x plus 2, that means that it's 2 raised to the x plus 2 power up here. And so now, if we look at our table of points and match up with these points we already have, second in graph gets us our table of points. Okay, so if we look and we match those up, we know what these y values are, and look where they start. So at -3 as a matching x value for this, we have 0.5 or 1/2 here. At -2, that's where we have our +1 as our y value, right? And think about that. It went from 0, 1 to -2, 1. We moved back 2. So now we have -1, 2, because we move back 2, and 0, 4. Well, that makes perfect sense because this moves back 2, moves left 2, 1, 2, boom, there's 0, 4. We were just saying this moved left 2, 1, 2, there we go. There's -1, 2. This moves back 2, left 2, 1, 2, boom, there we go. There's -2, +1. See that? That's what we're looking at. Oh, sorry. I put those on the graph and we did not see them. So hold on. There you go. See those? We moved left 2. Move from this. Left 2. Left 2. Left 2. So really, I could figure these y values out by just taking the original function and moving it left 2. So now I know that the matching y value for a +1 is a +8. Now I can do, okay, this was 416. We need to move it left 2. Now it's 216. Okay? And to fill in the rest of that, I am going to want to look at that graphing calculator because these are points that don't fit on my graph. So 332 and 464 are just too big to fit on this 20 by 0 grid, right? They're just too big to fit on that. But what I can see is that pattern, and I can see that that asymptote did not change because I did not change by adding anything to the end of the equation. So now, and this was the point I kind of stopped at, now we're going to go back this direction, and actually let's fill in our asymptote in red because it is the same. And this was if we add f of x plus 2 inside the parentheses. That's the change we made. Now, what if we add 2 outside of the parentheses? Well, that's going to take our blue parent function and it's going to move everything up 2. Okay, so according to the first picture we saw, if we make the change outside the parentheses, that will add or subtract on the outside of the equation, moving it up and down that way. So now let's kind of prove that with our graphing calculator. So I'm going to go back to y equals. Okay, I'll leave the blue and the red for right now, but let's arrow down to y4 because it has a color involved, and I'd prefer to have a color rather than black on the screen. Okay, so let's do y4 with this, I think they call it magenta, but we'll call it purple. Let's type in 2 raised to the x, and then arrow right for your +2 because it cannot be in the exponent. This is not the same as the red one. This is not the same as that original red one. This is down here, which means that the whole function moves up 2 places. So when you press graph, you'll see that. You can see those original 2 functions that have their asymptotes down here, but look, our asymptote has now moved up to y equals 2. And then all those points have moved up accordingly. So I will show you the table in a moment, but let me show you how we can determine it right here on our paper. So let's take this point and let's move it up 2. Let's take this point on the original parent function and move it up 2. Let's take this point on the original parent function and move it up 2. This point, up 2. All our points are going up 2. All our points are going up 2, right? So this now is like 2.5. And this one right here is 2.25. And this one is 2.125. And so I'm going to stop right here and connect. And what do we notice? Our asymptote has come up 2. So this asymptote is y equals 2. This time, because we've got this end number 2, we've got an invisible barrier that we cannot touch or cross. Okay, I just wrote the change right up here. And now I just need to determine what are these new y values, right? So looks like this y value, I'll start with the y-intercept. Looks like this y value is 3. Okay, well, that made sense. What's 1 plus 2? 3. Okay, let's look at this y value. So for 1, it's now up to 4. Okay, well, that made sense because 2 plus 2 is 4. For 2, it looks like it's now up to 6. That makes sense. 4 plus 2 is 6. Now up to 3, looks like it's at 10, and that makes sense because the original y value was 8. We add 2, we get 10. So 16 plus 2 is 18. See that? And if we're adding 2 to 1/2, well, then this is 2 1/2. And if we're adding 2 to 1/4, well, this is 2 1/4. And adding 2 to 1/8, well, this is 2 1/8. And on our graphing calculator table, we can see that change happening. So second in graph gets us to the table of points. And you can see that 2.5, 2 1/4, 2 1/8. Okay, so these tables are matching up with exactly the movements that were happening on the graph. Okay, so we know based on that general form what the changes were supposed to be. Okay, so we can tell based on the general form, or we can tell based on plugging it in to the graphing calculator. But either way, we want to be able to describe what happened. All right, so right here, right, we were adding 2 to the outside, so that's what I labeled the purple function right there as. Okay, so now below, let's describe the changes that occurred. Okay, right here. When we added 2 inside the parentheses, that was our red one, the changes in asymptote, we moved left to y equals 0 was still my asymptote. Okay. When we made the changes here, it's plus 2 at the end, so we moved up 2, and our asymptote is now y equals 2, because that number at the end determines the y value of my asymptote. Okay? So we're going to look at what the general function notation would look like versus what the equation will actually translate to do. Okay? So if you're looking at the function notation to move left, you take f of x and you add, we're going to call it k, as our value. What does that look like in the actual function equation? So let's call it f of x plus k right here as well. That will equate to 2 to the x plus k value. That moves you left when you add inside the parentheses. It does keep your asymptote at y equals 0. All right. Right would then be, if I want to go right, well, that will be the opposite sign inside the parentheses, right? So f of x minus k will look like 2 raised to the x minus k power, and your asymptote will still stay y equals 0 because we still do not have a value right here that we're adding or subtracting. If you want to go up, it's just f of x and then plus k on the outside. Okay, so what will that look like in translation? And again, I'm using my original parent function to make these translations, right? So what will that mean? It'll mean adding 2 at the end. So 2 raised to the x plus k power now means that your asymptote is y equals k. And then this last one down here, f of x minus k will move you down k values, right? And what that will look like in practice here is going to be 2 to the x and then minus k here, and your y equals negative k, because we moved down, is going to be your asymptote. Okay? Cool. Good place to stop.